This is a video about a bar chart, which is this bar chart, which is a representation of a world that we can move around in. I'm going to the corner so that when I turn around, hopefully I have a nice view of the world. And this is fine. The technique I'm using to make this bar chart, to make this image, is called raycasting. And raycasting is easier to understand if we look at this world from above. Where here we have the player and we have a few walls with different colors. And these green lines represent the player's field of view. So inside these lines is what we can see. And to make this image, we divide this field of view up into many different directions. These directions are on the x-axis here. And we cast imaginary rays in every direction until they hit a wall. And rays which travel far before they hit a wall, such as these ones, we represent them, their directions, with small bars. Whereas when a ray is caught by a wall at a shorter distance, such as these ones, we represent them with bigger bars. And we have some very big green bars here because some rays, imaginary rays, in our field of view are caught by this green wall directly in front of us. And visually, that's how this raycasting works. But we have the formulas over here on the left and their workings. And we can click, for example, this is the map, this is a representation of the world, where 0 means no wall and a number above 0 means a wall. This is a formula that looks up the map, and many formulas here. We're interested in what we're seeing here, which is ray inverse distance, which we can get by clicking. Ray inverse distance is 1 divided by ray distance. And this is the relationship that gives us the effect that I described, where rays that travel far are smaller. It's because of ray distance being on the bottom here. The really interesting calculations are to calculate this ray distance. And here we have 6.33, and we have the minimum of 2 distances multiplied by fisheye correction adjustment, which we can turn off. It's not relevant to distance. 6.5 is the minimum between 2 distances, 6.5 and 7.4. The first time I coded this any raycasting algorithm, I took a naive approach. I traveled a short distance along the ray and checked if I hit a wall, and continued, repeated that. And I needed to repeat it many times because I didn't know where a wall was. This is the problem. And so I needed to do many checks to make sure I didn't skip a wall. And I needed to repeat them for all of these different directions. And so not only was it was quite inefficient and slow, and these calculations need to be updated every time a button is pressed. The image was also less smooth than what we see here, because I wasn't getting exact intersections with walls. This algorithm is much better than what I coded first. And it takes advantage of the fact that in this world, we can only hit a wall. A ray can only hit a wall at these horizontal grid lines or these vertical grid lines. And so we only need to check rays against intersections with horizontal and vertical grid lines. And so this distance is the minimum of two distances. One which is a distance between the player and where a ray intersects with the vertical grid lines. There's one vertical grid line right here, but there's no wall there, and so we continue to the intersection with the next vertical grid line, and there's no wall there, so we continue and we check the next vertical grid line, and there is a wall here. That gives us a point from which we can calculate a distance using Pythagoras' theorem, 4.37. But that isn't actually the distance that is used, because this distance is smaller, which checks against intersections with horizontal grid lines. This is the first one we check. No wall, we continue. No wall, we continue. Wall. This gives us a point, and the distance to the player is smaller. That is how we calculate these distances from which we can generate this image. So that's visually and looking at formulas how raycasting works. But there was a bug. We can travel back in time, so otherwise it might be hard to find. This does not look right. At the corner of this purple box, we should have a straight edge, but for some reason we have a small bar here, which makes no sense. And if we look at the ray for this, the corresponding imaginary ray, we can make sense of what's happening. The ray is going through the wall, and we're only catching it on the other side of the wall. And we have over here the formulas and the workings, so we should be able to use them to figure this out. So this distance, and there's a check here, check here, check here, and all of these are returning no wall, but I think that this one looks like one that should return a wall. So let's click on it, and here we get a hit, here we don't. So I'm wondering why this function is returning 0 when I think it should return something. So let's go in here. And there's a boundary check, right, for outside the world. That's not relevant. And we're looking up the map at some point where the floor of y minus something that I call a necessary fudge, floor of x minus something. So this is interesting fudge. This is right at the corner, and so 4 point a little bit is where we are, and this fudge is going to affect checks that are right at the corner, and in this case 4 point a little bit will become 3 point a little bit. The floor will change, so this fudge might be a part of the issue. We can say make it 0. Now that didn't work, we're missing some walls here, so perhaps I was right to say it was a necessary fudge, at least the way I've coded this. If we can't make it 0, then maybe we can make it smaller. Nothing changed there, and if you change this one. The image is fixed. If we click on the bar again and look at the other distance calculation and the other check at the edge, this is actually the one that was causing an issue. It was actually here. But the fixes it anyways. It's the same fix. And we can see the correction here also. We can continue playing. In fact, we should look for regressions. It helps. We can replay some gameplay. Everything looks okay. Fisheye correction, I'm going to turn that back on. In fact, I'm going to show what that does. This ray is further away than this ray when it hits a wall, but we don't want this effect to show up, and so a little bit of trigonometry in here gives us pretty much equal heights. So it's a correction which makes this like a little bit more than a distance, but it's okay. And another thing we can do in this world and in this environment and with these formulas and with these workings, we already saw changing the formulas while we're playing, while we're in the middle of something, changing them in context and seeing updates. And that's kind of interesting for games, that we can change the world that we're playing in. And make our own little levels. So this video is about a bar chart, but it's also about a connection between representations of numbers, which is what a visualization is. A connection between representations of numbers, their formulas, and their workings. And using a strong connection between all of those to understand an algorithm and find a bug and fix an algorithm. Which this connection is something that I'm exploring with calculang.